I'm so happy to be in Warsaw. I can't believe I'm here. When I was a little boy, my mother and father loved Polish art, and our house in the United States is filled with paintings, rugs, tapestries, all from Poland. And when I was a little boy, I thought that the pictures of old Warsaw were so beautiful hanging on our wall. I told my mom I wanted to go to Warsaw. I wanted to see this in real life. This was 27, 28 years ago. And she said, for an American, that would be very difficult. I don't know if that's a place that you'll ever be able to visit. And that made me so sad. And so I think it's absolutely amazing that I'm here today. I'm so happy. I'm also happy that I'm talking to you at a science museum. I think that this science museum in particular is doing an amazing job of showing children and students that science is all about discovery and engagement, puzzle solving, and figuring things out. This is, I think, a model for what science education in our classrooms should look like. We should be engaging students the way they're engaged in a science museum. And so that's going to be a major theme of my talk today, how we can make the science classroom environment more like the science museum environment. I want to talk about 4 main points today. The first is I want to talk about what I see as 2 very different aspects of science. The products of science that we memorize as facts in a textbook, and the process of science, which is the long, puzzle-solving job that scientists do to figure out those products in the first place. I then want to talk about how teaching the process of science, teaching the thought process that scientists do, I want to talk about why that is so critical. I also want to share with you why I feel that textbooks and many elements of traditional science education often prevent students from being able to engage in this process of science. They prevent students from being able to engage in solving puzzles, in critical thinking, and most importantly, in discovery. And lastly, I want to provide some examples and strategies for how teachers can incorporate the process and discovery of science into their own classrooms. First, a little bit about me. I find it very ironic that I'm standing in front of you talking about education, and particularly science education. Because when I was a teenager, when I was in high school, I hated school. And I particularly hated science. I saw science as nothing but a bunch of facts in textbooks. I had many little paper note cards. A word would be written on the front, and a definition would be written on the back. I'd try to memorize card after card. I hated it, and I had no idea why it was important. I had no idea how it affected my life. Instead of working on science or studying for school, I enjoyed fixing my car on the weekends. I enjoyed helping my father plant crops and figure out what sort of fertilizers or what type of watering regimen would get us the biggest pumpkins or the best heads of lettuce. I hated school and I hated science until I had one biology teacher. This biology teacher, he taught differently. He asked us, one of the very first days of class, what do plants eat? I didn't even really know what he meant, so he elaborated. He talked about all the food that humans have to consume and put in their bodies to grow. The pounds and pounds and pounds of pizza and bread and chicken and steak and salad that we eat that goes to build our bodies. And he asked us the question, where do plants get that nutrients? A giant tree weighs hundreds and hundreds of kilograms. Where has it gotten the food and nutrients to build its own body? As a 15-year-old, I confidently answered, the plant is absorbing all of its nutrients from the dirt. It's eating dirt. And most of the mass of a tree, of a plant, is coming from the dirt that it's eating and it's pulling up through the roots. It made perfect sense to me. I even remember pounding the table afterwards saying, yes, it eats dirt. So he said, great, prove it. You said that the plant is eating dirt. Prove it to me. And for the first time ever in school, I made a series of facial expressions that looked sort of like these. For the first time ever in school, I had to think. And this is what it looks like, what a student is thinking. When a student is memorizing definitions, they don't look like this. But this is the face that students make when they're solving puzzles, when they're trying to figure out concepts, when they're faced with a new fact that they need to discover. I thought and I thought and I thought. And I finally figured out that we'd take a little pot of dirt and plant a seed in it. Actually, the seed had already grown to a small little plant. We'd put the small plant in the dirt. Oh, I'm sorry. First, we'd weigh the dirt. Weigh the dirt and find out the mass of the dirt. Then we'd add the seed. Wait for a couple weeks, allow the plant to grow, and then remove the plant, shake the dirt off the roots, weigh the plant, and weigh the dirt. And I was shocked to find out that the dirt weighed exactly the same as it started. Yet the plant now weighed more than the mass of the dirt. How was this possible? Because the plant was eating the dirt. The plant was eating the dirt, but somehow the dirt was still there. And I realized from the first experiment that I had ever done that plants do not eat dirt. Instead, I was confronted with a mind-altering realization that plants can take liquid water and the carbon dioxide from our breath and pull it in with the help of energy from the sun and make wood. And not only that, but that I had figured part of this out myself. I had discovered that plants didn't eat dirt. And from that point on, whenever I see a piece of wood, I think, wow, that was made from people's breath, from the carbon dioxide in people's breath, made that wood. Amazing. We didn't stop there. The next question that my biology teacher asked was, how does the color of light affect plant growth? And again, for the second time in school, I thought and I thought and I thought, this time with a team of my friends. We came up with this idea. We'd take a number of small plants, all the same size, and we'd take a variety of light bulbs. We'd go to the school theater where they had different colored filters for the light so that we could make each light bulb shine a different color. We'd put the different colored lights above the plants and we'd let them grow. And look at this. We found that not every color allows a plant to grow equally, that the plants were growing best in violet light and red light. The next question that my biology teacher asked was, okay, why? What's going on here? Prove it. We thought that this might have something to do with the plant's ability to pull in, to absorb lights of different colors. And so when we told our biology teacher about that, he told us about an instrument called a spectrophotometer. And the spectrophotometer allows us to take a sample and see what different colors of light it absorbs. We took leaves, we crushed them up into a liquid and put it in the spectrophotometer and found out what colors of light the leaves were absorbing and which they were not. And look at that. We came up with a graph very much like this, found out that they were absorbing red light and violet light, and the color of the light that the chlorophyll in the plant leaves was absorbing was almost perfectly correlated to the different growth heights that we saw for different colors of light for our plants. This was the second coolest, mind-altering experience that I had in school. To see that we could go from a physical property of the world, that we could go from different heights of plants under different colors of light, that we could do an experiment with an electronic device that would give us data that would explain why plants grew different amounts under different colors. It was the first time that I understood how science could let us ask and answer questions about the world around us. It was at this point that I decided I would have no other choice in life but to become a scientist. Now, of course, this information that we learned, it was in the textbooks that were sitting on our desks. Most of us weren't reading the textbooks because they were filled with complicated jargon words that were incredibly difficult to understand. The textbook itself was so boring. We could easily have looked this up and found graphs similar to the ones that we discovered for ourselves and found information about photosynthesis that told us that plants didn't eat dirt. But the process of figuring this out activated a part of my brain, an excitement in me that the textbook reading never could have. Now, before I go on, I just want to point out to you how both of these experiments are actually quite easy to do in your own classes if you teach life science, biology, or chemistry. To do the first one, all you really need is a little bit of dirt, a pot, and a scale. And for the second one, all you need is some lights of different colors and a spectrophotometer. If you don't have a spectrophotometer, you can make one using a smartphone and about $1 worth of materials that you can buy online. If you search the internet for cell phone spectrophotometer, you can get instructions for how to make a very simple, very reliable version of one using just a smartphone. So, the next school year, you could share both of these experiments with your own students. Going back to me, I eventually went to school for science and studied biology and chemistry in university, but I never forgot how inspired I was by my high school biology teacher, and so I decided to teach myself. Since I've entered the classroom, I've moved back and forth between doing research and teaching high school. Most recently, I've been pursuing a PhD in microbiology, which I just finished, and each summer I would teach summer school students from around the United States who would come and visit Boston, where I was working for the summer. So I was both doing research in the lab and also teaching science. Now, I'm involved in a number of things besides just teaching high school and doing research. I'm very interested in science communication. I like to talk a lot about how we can make science more engaging, and I also make a wide variety of video lessons about physics, chemistry, and biology, which I put on YouTube. I've been so happy to hear that, at least in English-speaking countries, an increasing number of students, teachers, and schools are using my videos instead of the textbook. And this makes me happy, not because they're my videos, but because when I'm teaching topics, I always try to cover them with an eye towards discovery, towards engagement, and towards making this material accessible. When I'm in the classroom, though, I always try to share as much as I can from my research background with the students. Maybe it's reading new articles with them in newspapers and magazines. Maybe it's sharing information about new drugs or therapies, new information that we have about curing diseases, or occasionally information about the environment that's affecting us in the United States. One day, we were talking about microbiology, which made me so excited because it was my field. It's what I study all day. And so I showed my students a number of the pictures of the microbiology lab where I work. There were pictures of the various rooms, the chemicals we use, the equipment we used. And a number of students looked at these photos skeptically. One of them asked a question that changed the way I thought about teaching. She looked at these photos and she asked, "Where are all the textbooks?" I didn't even know what she meant at first. And then she explained it. She said, "Well, in science class, we have all these textbooks. We have these little note cards. We're memorizing terms. Why wouldn't scientists in their labs have rooms full of textbooks? Isn't that what scientists do? Don't they read and study textbooks all day?" And I realized that the way we had been teaching science would not have answered that question for her. I realized that she didn't understand that there is a difference between what scientists do and what science students do. She didn't realize the information from her textbook had been discovered by scientists who were doing science in the lab. She didn't understand that there were two parts of science: the active process of figuring things out and discovering, and then the products of science, the facts that these scientists discover. And I realized that the way I was teaching needed to take into account the difference between scientific process and products and engage students more in the activity of discovery. A little bit more about the process and products of science. I here want to describe the process as how scientists ask and answer questions about the world. This is a highly engaging, creative pursuit. It involves a scientific method. It involves experimental tools and techniques. It involves a tremendous amount of critical thinking, like the critical thinking that I did when I was back in high school, making that thinking face. It involves problem solving, collaboration, and creativity. It also involves students presenting, debating, and discussing their findings. Now, on the other hand, the products of science, more or less, are the results of the scientific process presented as facts in a textbook or a science course. A lot of times, students ask me, like my previous student did, what do scientists do that is different from what science students do? And I'm surprised by how many people in the general population ask me, okay, so you're a scientist, you study microbiology, but what do you actually do all day? What does your day look like? What is going on in your head when you're in the lab? So to better explain the difference between the process and the products of science, I want to give you a short 5-minute explanation of what I do in the lab that I feel quite accurately models the scientific process. Along the lines, I'm going to talk a little bit about the products of science, and then I'll show you the process for an experiment that I recently completed in my own lab. Here we'll start out with some products. These are facts that we already know, that scientists before me have discovered, that I can then move on from. I study microbiology, which means that for the most part, I study things that are far too small for the eye to see. Namely, I study bacteria and viruses. Now, many people don't know this, but viruses, there are many types of viruses that can infect bacteria. And when a virus infects bacteria, here's what happens. The virus attaches to the outside of the bacteria, and it puts its own DNA into the bacterium. Now, DNA is essentially like a blueprint. It tells living things what to make and how. So when the virus slips its DNA into the bacterium, it tells that bacterium to do a number of things. For many viruses, the first thing that virus DNA does is it makes things that destroy the bacterial DNA. So now the virus DNA is in charge of that bacteria. The next thing is the virus DNA tells the bacteria to start making more viruses. This continues as the bacteria cell follows the instructions on the virus DNA and makes more and more and more copies of virus until the cell becomes so filled with viruses that it bursts. In other words, the virus, by adding its DNA to the bacteria, turned the bacteria into a factory, into a machine to make more viruses. We can even see this process without the aid of a microscope with our naked eye. When bacteria are growing in a liquid solution, there are so many of them that the liquid becomes very, very cloudy. As you can see from this photo here, this yellow liquid has become extremely cloudy. It's filled with billions of bacterial cells. If I add virus and wait a few moments, that virus will infect all the bacteria and will split them open while it makes new virus. And I can see that because the liquid clears. All the bacteria that were living there are split open when the viruses burst out of them. So just to my eye, I can see what happens when viruses infect and kill the bacteria. Now, everything that I told you there was products. It was information that had been previously discovered that serves as a background for what we'll go into next. Here is the process. We'll figure out something new. About a month ago, maybe 2 months ago, I was doing an experiment with bacteria and viruses. I had two different types of bacteria. I'll call them bacteria A and bacteria B. And I was trying to infect them with a virus. I added the virus to this cloudy liquid that was filled with bacteria. I waited, and I found that after 20 minutes, after an hour, after 2 hours, the liquid was still cloudy. So I make that thinking face that I made when I was 14 years old, and I ask myself, what's going on here? Why isn't the cloudy liquid with bacteria turning clear? What's the matter? And I come to the conclusion that these two types of bacteria appear to be resistant to the virus. The virus can't kill them. They're not turning clear. I want to investigate this more. So I think, and the first thing that I want to know is, has something happened to the viruses? Are they still active and effective? Okay, that's my question, but how am I going to answer it? I think. And what I decide to do is use a type of bacteria that I know has been killed by viruses in the past. If I were using fancy scientific jargon, I might call it my control strain. I know that it should be killed by the virus. I take my bacteria strain S, which I know is sensitive, I add some virus to it, and bam, it's still cloudy. So what does this show? This shows me that the virus is no longer active. The virus can't kill the bacteria that it has killed in the past, which means that the results that I previously got, strains A and B, which couldn't be killed by the virus, this might be because the virus was just no longer active. I then go back, get new fresh virus, add it to the bacteria. And look at what happens. With my new fresh virus, my standard sensitive bacteria, it's killed. It turns clear. My A bacteria also turns clear, which means that it was not resistant. But my B bacteria, it stays cloudy, meaning that it actually is resistant. Bacteria B is resistant. And now because I'm a scientist and I want to know things, I want to figure out why bacteria B is resistant to the virus. So now I have to think back to the products of science to figure out where things could go wrong. Well, if you remember, the first step of infection involves the virus putting its virus DNA into the bacteria. So I want to ask, is the virus DNA getting into the bacteria? Maybe that's why the cell isn't dying, because the virus isn't able to add its DNA. In order to do that, I will mix together the bacteria and virus. I will then wait a little while, and then I'll separate them out again, and I'll ask, where is the virus DNA? To do this, I'll use a tool called a centrifuge. I can put a tube in a centrifuge, and it spins it. After a little bit of spinning, the heavier bacteria sinks to the bottom of the tube, and the lighter viruses stay on top. A centrifuge is a way that we can separate things based on their masses, and sometimes based on their densities. So that's exactly what I do. I infect the bacteria, the viruses, I let them sit there, and then I spin them out to separate the bacteria on the bottom from the viruses on the top. And I look to see where I find my virus DNA. Now here I have two graphs on the bottom. On the left, I have bacteria that are not resistant. And you can see that on the top of the tube, there's only a small amount of DNA. But on the bottom of the tube, towards the right, that's where most of my virus DNA is. On the other side, my bacteria B that's resistant, I find that most of the DNA exists in the top of the tube, and very little or none exists at the bottom of the tube. What are these results showing me? These results, these graphs, are showing me that the virus DNA is in the bacteria, in the S strain. But for my bacteria B, the DNA is staying in the viruses at the top of the tube. And the last thing that I want to do is take a look now and see if I can actually see visually what's going on. I will use a tool called an electron microscope, which allows us to take very highly magnified photographs at the atomic level. You can see an image here from an electron microscope that's showing some viruses that are attached to the outside of a bacteria. And when I look at the two different types of bacteria, look at what I see. The bacteria on the left have viruses attached to them, but the bacteria on the right do not have viruses attached to them. In other words, something has happened to the bacteria B that has prevented the viruses from attaching to them. That is why the virus DNA isn't getting into the bacteria, and it is also why the bacteria are resistant to the virus. Now, I'm telling you this story not because this particular thing that I discovered is of great importance to the scientific community, but because I think that it illustrates the steps that as scientists we go through asking and answering. Something happens, and then we want to know what the next step is. How will we use tools to figure this out? We get results, we scratch our heads, we think, and figure out what they mean. When we look at this in terms of process and products, we can see that there are very different aspects to this discovery process. On the left, the process involves lots of thinking. It involves using tools, designing experiments, looking at graphs, scratching our heads, thinking. It involves a tremendous amount of puzzle solving and critical thinking, problem solving. All of this active scientific thought, though, if this were to end up in a textbook, would be distilled to one single sentence. Bacteria can become resistant to a virus if their outer surface changes so that viruses cannot stick. That's all you get, right? The previous process involved so much puzzle solving and thinking. I saw some confused faces in the audience at first, but then as I explained more, I saw that many people began to understand my thought process. I think that some of you got a sense of how to think through the problem along with me. But if all I presented you were the products, the bacteria become resistant to a virus if their outer surfaces change, you wouldn't have had a chance to engage with that problem solving and critical thinking. This is why I'm often frustrated with how textbooks present science, because they tend to present only the products of science. In America, we have a publication called TV Guide. And TV Guide, every week, gives you you can buy TV Guide at the supermarket, at the drugstore, and it's this little book. And it gives you a summary, a 1 or 2 sentence summary of every television show that will be on television that week. For example, Jason gets to know Violet in vampire camp. Sarah is desperate to keep True Blood flowing. Sookie Mole's brokering a deal between Warlow and Bill. If this were all you got from TV, why would anybody want to watch TV? Right? Like, this is what textbooks do. Textbooks are like TV Guide. All they give you is the summary. It would be like we said all you can do is read the 2-sentence description of the TV show in TV Guide, but you can't watch the TV. Why would anybody ever want to do that? But I feel that that is exactly what science textbooks do. Instead of giving us the full TV show, they give us the 1-sentence summary. Instead of the tears that we cry when a terrible disaster strikes our hero in a TV show, and the joy that we feel when they finally fall in love after 3 seasons, we get 1 sentence. Bill and Anna fall in love. Just like some bacteria can become resistant to certain viruses by altering their exterior surfaces to prevent viral attachment. What a drag. Like, it's so boring. But the process of science can be so engaging. I get frustrated when I see science textbook writers not always understanding this. In the introduction to this biology textbooks that I've been talking a lot about, the author writes at the bottom, you don't need a lab coat or a degree or a laboratory to be a scientist. What you do need is an inquiring mind, the patience to look at nature carefully, and the willingness to figure things out. I think that is an exceptional description of the scientific process. But I can also say quite definitively that this textbook never allows students the chance to look at nature with an inquiring mind or the opportunity to figure things out, because it always gives them the answer. It gives them the 1-sentence TV Guide summary without letting them watch the TV show. As I was a teacher and coming to terms with this, I was realizing that there was scientific critical thinking going on in my school, but just not in science class. I don't know about in Poland, but in the United States, students love playing card games with They involve strategy, and they usually involve fantasy with wizards and dragons and that sort of thing. Students will love this, and it involves tremendously strategic thinking with problem solving and puzzle solving. At my school, students in the Latin and Greek club would build catapults and other ancient pieces of war equipment, and they would scratch their heads and figure out how to build them best. Even I think many smartphone games that require students to think critically. Oh, I have to cut this rope so this will swing down and will hit the balloon, which will raise it back up. Even games like that require much more thinking than my own science class that I was teaching did. More than anything I found was what was going on in the automobile maintenance courses in my school. I knew that I had a big problem when one of my favorite students said that he was dropping out of the science preparation classes because he felt that he was using his brain more in the auto mechanic courses. But when I dropped by to see what was going on with the students learning to fix cars, I understood exactly what he meant. The process that the auto mechanic students were using was exactly the process that I would use when I was in the lab. A car won't start. Okay, is there enough gas? How will I test that? Okay, there's enough gas. Is there a charge in the battery? How will I test that? Okay, there is a charge in the battery. Is the starter motor running? No, it's not. Okay, so what do I do now? Is the problem that the starter motor is broken, or is electricity not reaching the starter motor? How will I figure out if the starter motor is working? How will I figure out if electricity is reaching the starter motor? And I realized that the students in the auto mechanic class were doing much, much, much more scientific thinking than my students who were apparently headed to college to be scientists, to be physicians. My students were doing much less scientific thinking than those in the auto class. And of course, I'd be remiss to mention how much amazing critical thinking and puzzle solving goes on in science museums. I mean, look at the expressions on these people's faces. These are the figuring things out expressions. So I feel that we need to focus more on teaching the process of science. And I want to finish this talk by describing some of the ways that we can do that. But here are what I feel the 5 most important reasons why we need to think about teaching process to our students. First of all, this was very difficult for me to come to terms with as a science teacher. But the sad truth is that students will quickly forget most of the products they learn from textbooks or science courses. I know this because I know it to be true for me. Despite the fact that I just finished a PhD in biology, I recognize that I have probably forgotten 90% of the information of the products that I learned in science classes over the years. What I did retain, though, was the process, the scientific thinking, and the critical thinking skills that students can learn by thinking through problems aren't only useful for people like me who are going to become research scientists, but they are useful whether someone is planning to become an electrician or a car mechanic or a physician or a gardener or a lawyer or a professor. Critical thinking skills are transferable to a wide range of disciplines. Third, this was certainly the case with me. I feel that individuals enjoy critical thinking, puzzles, and problem solving so much more than memorization. What got me excited about science for the first time wasn't learning the information from the textbook. It was a chance to solve a puzzle asking what plants eat. And I feel that students naturally are drawn to challenges and experiences that allow them to do critical thinking. Fourth, I think it's a shame that students who may want to become scientists when they grow up aren't given an adequate chance to see what real science looks like. I think it's a problem that students in my own science class think that scientists just read textbooks all day for two reasons. Maybe a student loves reading textbooks. Unfortunately, they wouldn't be a particularly good scientist, having to think through problems and problem solve, often in collaborative groups all day. The student who likes reading textbooks on their own often isn't the best group collaborative scientist. But at the same time, and this I think is a bigger issue, students who don't enjoy textbook reading, who would rather become auto mechanics, might be brilliant scientists if only they had a chance to see what scientific thinking was really all about. So I think we owe it to students who are considering a career in science, math, engineering, and technology. I think we owe it to them to show them what real science thinking looks like. And finally, without understanding how scientists actually think and arrive at their conclusions, members of the public don't really understand how scientific information is created. I don't know about in Poland, but in the United States, we have tremendous difficulty with scientific misinformation spreading throughout the country. And much of this is due to the fact that members of the population don't understand that scientists think through, collaborate with each other, and arrive at conclusions. They think that if you just read something in one textbook, it might be true, it might not be, and if another textbook says something else, that these different options are open to debate. I feel that if members of the public understood how scientists arrive at their conclusions, they'd be much better equipped to understand how consensus is reached in the scientific community. So I want to talk about a few ways that we can restructure instruction so that students can learn, enjoy, and engage with the process of science. As I've said before, though, for my TV guide example, one of the problems I feel is that textbooks and traditional instruction can ruin the fun and challenge of discovery by giving students the answers right away. And one of the things that we need to do as teachers, if we want our students to engage more fully with the process of science, is to hide these answers until the students are allowed to discover them themselves. For example, from a physics textbook, it says, for objects of any mass, downward acceleration due to gravity is equal to, that should be negative 9.81 meters per second squared. There it is. There's the answer. That's the product. But we could engage students in the process before just telling them the answer. The process might look like this. It might mean making a new worksheet or material for the students that first asks, what happens to the velocity of objects as they fall towards the ground? Does the velocity speed up? Does it slow down, or does it stay the same? Prove it. This is an incredibly powerful thing for students to be asked. They can memorize that the acceleration due to gravity is negative 9.81 meters per second squared, but many of them don't even intuitively understand what acceleration is. But when you ask them, find out what happens to the velocity of objects, now they have to solve a puzzle, and now they have to understand the ramifications of what they're discovering. I've had students do this in the classroom, and we have so much fun. Some of them use stopwatches. Others use the video functions on their smartphones to take videos of objects that are falling down. Some use more traditional physics equipment like photo gates, various devices that turn on and off, that have a beam of light and turn on and off when something goes through that beam. One of my very ingenious students decided to do this with sound. He took a board and put strings at regular intervals down the board and had marbles roll down the board. And what he heard was the speed increasing. It was so cool. it would go, as it fell, do, 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 and he could hear the acceleration. The point is there are many different ways to do this, but when students were engaged to figure this out for themselves, they came up with a wide range of creative solutions. And then from there, we can continue, asking if objects of different masses are drawn towards the ground at the same rate. Take out the camera phones, take out the stopwatches, do whatever you want. Find a way to measure the velocity at which an object moves towards the ground, and then find a way to measure the rate of change. Now, students using a stopwatch or a camera phone or photo gates may not come up with a figure negative 9.81. We can always fill that in later. But as long as they get close, and you may be surprised how close they can get, as long as they get close, they are doing so much more cognitive development than if they were to just read that information and memorize it from a textbook. You know, many lab activities often ask students to confirm variables or give them long step-by-step instructions, but I'm not sure that these are necessarily the best at teaching process. I remember when I was in college, we were given an assignment to use the following equipment to confirm that acceleration due to gravity is equal to negative 9.81 meters per second squared. Like, that's okay, but it's not particularly exciting to confirm a number that is already given to you. It's much more exciting to discover that number for the first time. When I started out teaching, I loved to give my students very complex labs. But the longer I taught, the more skeptical I became. Just because a student is doing a long piece of work doesn't mean that they understand the underlying science. It doesn't mean that they're doing problem solving or critical thinking. I've reminded of something that one of my students said once when he said, 2 drops of this and 5 milliliters of that, and I heat the tube and then put it on ice, and I have absolutely no idea what I'm doing or why. And unfortunately, this was very representative of my own science lab experience when I was in high school and college. I feel that sometimes the simplest and easiest labs can provide the most scientific thinking. And I always like to think about this puzzled face. When students are doing or planning a lab, are they just following instructions or are they working through puzzles? How can you tell? You look at their faces. If they're just adding 3 drops of this and 5 milliliters of that, they look like people following a recipe. If they're trying to figure out how to measure the acceleration due to gravity, they look like that. They're thinking. They're problem solving, they're engaged. Just because students are going through the motions of science doesn't mean that they're actually doing it. I'm reminded of a friend of mine who trains, he's a pianist, and he trains competitors in this beauty contest. It's called Miss America. He trains them how to pretend to play the piano, because to be a contestant on Miss America, you have to have a skill of some sort. And so he trains these women who are on Miss America to learn how to play one song on piano. And they're very good at it. But it's just one and only one song. And I think of these people in the beauty pageants playing their one song. They may look like musicians, but it doesn't mean that they actually are musicians, that they're thinking like musicians, that they could learn any other piece of music. And I think that we should keep in mind this Miss America story when we present laboratory exercises to our students. Just because they may be going through the motions of adding a few drops of this and a few milliliters of that doesn't mean that they're actually doing the scientific thinking. They might be playing the experiment the same way a contestant on the show is playing a piano. Don't be fooled by pouring liquids. Always look for the faces that show thinking. So we could say that, a few basic concepts for shifting from products to process is find ways for students to discover some of the facts that appear in the textbook. We can present students with real hands-on lab activities, like estimating the acceleration due to gravity, or we can give them simulated data for analysis. I'll talk about that in a minute. And obviously, from a teaching standpoint, activities like this can't be done every day. Absolutely not. But likely once per week, I bet once per week, there's a topic that we can cover this way. The information that is discovered doesn't have to be new to the world, just new to the students. And I do worry about this sometimes when I hear various educational organizations talking about problem-based learning and inquiry-based learning. There's often a sense that students have to be doing brand new, original research in order to be considered to be learning science. They don't have to be discovering information that's new to the world. Everybody knows what acceleration due to gravity is. But if they're discovering it themselves, that's what matters. And finally, if you plan to have students learn a concept through process, be careful. Don't let the textbook give it away first. Here's an example of this. We're talking about independence of motion here. The idea that movement in the x direction doesn't affect movement in the y direction. But as textbooks often do, they give this information away right away. They say in the horizontal direction, motion continues with constant speed, assuming there's no friction. And in the vertical direction, velocity speeds up with constant acceleration. Great, you gave away the point. But we could ask something like, often, when someone is going to jump into a pool, they will run very fast before jumping to extend the time they'll be in the air. How does horizontal motion, the running, affect the time it takes to fall vertically? Prove it. Well, it doesn't. But everyone thinks that it does. And so giving students this kind of opportunity to prove this commonly held misbelief can be tremendously useful. Now, because textbooks always like to ruin the excitement, right after this discussion, there is a picture of this very thing happening. It would take 5 to 10 minutes for students to come up with this sort of an activity, but when it's given in the textbook, it spoils all the fun of discovery. Something that I like to do is have students discover these basic elements of science, but then write their own textbook sections to pretend that they have discovered this, and now they are going to write the textbook. And suddenly when they do that, when they summarize their findings in a way to communicate them with others, they understand where the information for the textbook comes from. They understand the information from the textbook is just facts that have been distilled or taken from scientific process. One of the last things that I want to impart is that students don't always even need to generate data themselves to use problem-solving skills and participate in the process of science. For example, Boyle's law talks about how volume of a gas and pressure of a gas are related. Now, some schools have equipment like this that allows students to actually do hands-on activities, but at the same time, you can just make data and give it to the students to analyze. No, they unfortunately won't have the opportunity to go through and put more pressure onto a sample of gas. But when they get numbers, they can still go through the process of data analysis to figure out what the relationship between these variables is. This is particularly useful in things like electricity and magnetism in physics, for things like circuits and electricity. We can't always provide the students with the opportunity to experiment with these variables or with these concepts, but it is quite easy to give them simulated data and then allow them to analyze it and reach conclusions on their own. However, again, we have to be careful that the textbook doesn't just ruin the surprise. In this textbook, for example, right after they present the pressure and volume data, in the next table, they show how to realize that pressure times volume always equals the same thing. This could be a very powerful thought exercise for the students to come to this realization themselves and to derive an equation, but when the textbook gives them the analysis, they're not able to be engaged. One of the last things that I want to say is that many times the actual experiments can be too hard or complex to understand, but the basic products can still be presented as a puzzle. In chemistry, for example, when two atoms are connected by a bond, that bond can be polar or nonpolar, depending on how electrons are shared. But very confusing for students can be the fact that even if a molecule has a polar bond, that molecule itself isn't always polar. Nonpolar molecules and polar molecules can both contain polar bonds. Now, the experiments that it would take for a student to figure this out are very complicated. But this basic information can still be presented in a way that allows students to do problem solving. One of my favorite activities in science, in my chemistry class, is to give students a list. Here are all the molecules that are polar, and here are the molecules that are nonpolar. Now you decide, figure out, tell me what makes a molecule polar, what makes a molecule nonpolar. I love doing this exercise with my students. They draw out all the molecules. They think, they make the face. They think, and they finally realize symmetrical molecules are nonpolar. When the charges are symmetrical, they are nonpolar. When the charges are asymmetrical, they are polar. The point is, this involves some very complex bonding theory that students couldn't necessarily understand the actual experiments for. But the basic information can still be presented in a way that engages the students to solve through a puzzle. My students who do this exercise will never forget this information because they didn't just memorize a fact from a textbook, they discovered it themselves. And finally, many experiments that we could never, ever do in the classroom can be summed up quite nicely in this sort of a simulation. I don't have time to go through this whole thing, but this is one of the earliest experiments that showed that DNA was the hereditary material, that it contained genetic information. It involved injecting different types of bacteria into mice and seeing whether they live or die and reaching conclusions based on this. It's an experiment that is easily understood by a 13-year-old or a 14-year-old. It's something that they would never be able to do in the classroom. But when it's broken down by a teacher step by step in a simulation like this, students are challenged to do some critical thinking and figure out what's actually going on. And by constructing an assessment like this, teachers can share this type of experiment with students and still get them to come to conclusions looking at the data. It's similar in a way to the information about bacteria and viruses that I told you earlier. You didn't have to be there in the lab with me, but still you were able to do some of the critical thinking and problem solving involved. So, to summarize this up, I would say that to create materials that teach the process of science, it makes sense to go through the curriculum and identify some of these topics that students could discover through hands-on inquiry or simulated data. Where do we get this information? Well, often Wikipedia and more advanced textbooks contain information about the experimental process that was used to discover the information in the first place. So often you need to look no further than Wikipedia to find information about these original experiments. Often you can make up simulated data on your own. Now, science museums and university instructors, teachers, and students can be tremendous resources. In the United States, partnerships between schools and colleges and universities are very common. I don't know if such partnerships are common in Poland, but it's fabulous to be able to get university professors and students into your classroom to help you design materials that show students how to do this sort of critical thinking. Any graduate student in science, any professor in science will have so many examples of critical thinking puzzles and problems that they'd be happy to share them with you. There are tons and tons of them. So those sort of partnerships can be great. And remember that simple is often best. just get the students thinking. So I hope that I've shared a few pieces of information with you today. And I hope that I have convinced you about the importance of scientific process and products. That students may forget the products. And in fact, many of them always will. But it's the process of problem solving, of critical thinking, of scientific inquiry that will stay with the students, and it will be applicable essentially to whatever they do in their professional lives. I hope you can see ways that we can create environments in our own classes to engage students in this type of inquiry. Often that means pushing the textbook aside temporarily. But once the students learn the information on their own, we can pull the textbook back in to clarify things that they may not have understood, to reinforce knowledge, or to fill in gaps. And finally, I hope that a big take-home will be how amazing, how engaging, how fun it can be for students to approach science as problem-solving instead of just memorization. It certainly changed my life. A brief experience that I had when I was young in science class changed my life. It got me excited about science, and it showed me the beauty of inquiry. And I hope that all of you have a chance to share something similar with your students. Thank you very much.